Hello everyone, I am Harold Hastings. This is my partner Alexander Zuleta. We will be doing a shape memory alloy passive shock absorber.
Well, the purpose of our design is to implement a variable absorber, shock absorber, which can vary the damping ratio by changing the temperature. We're going to implement a hidden system, and we're going to try, and we believe that it's going to effectively attenuate high amplitude vibrations. Our approach is to analyze a 1 degree of freedom system. So we're going to have a mass, we're going to have a spring, and one damper. The damper is going to be made out of nitinol. Nitinol undergoes phase transformation, so we're going to absorb some energy through latent heat. And so what we're going to do is we're going to analyze a transfer function. We're going to sense the input and the output. And we're going to see how is the transmissibility of displacement from one side to the other side. In order to know if the material can behave as a spring, we found the resilience number, which tells us if the material can go back to the same position. So we tried to compare the standard alloys, steel alloys, and see how the resilience is close to them. And we found out that it's high, so nitinol can work as a spring. We're going to implement in our calculations a function. It's the shear. The shear is going to change with temperature. So what we're going to do is we're going to put this function inside this other function. I'm going to tabulate to find what are the wire diameters for our scale model. Since nitinol has a different Young's models as it increases temperature, we have from 40 to 70 gigapascals in change. So we can see what is the K at 40 gigapascals and at 70 gigapascals. Our design is going to consist of a top shell and a bottom shell. Those shells, they're going to slide one relative to the other. We're going to have the springs made out of nitinol. They're going to undergo phase transformation when they're compressed. We're trying to put high pitch, so we're sure that the material goes to a high stress. As we see here, the red plate is going to also travel relative to this bottom shell. So everything is going to move relative to the other. Nitinol comes in different alloys. We're researching what is the appropriate one. We determined that martensitic is the right one. Martensitic shows very good damping properties. It gets hot when it gets compressed, so some of the mechanical vibration is transferred into heat. It goes from martensite heating, becomes austenite. When cooling, it goes to martensite again.
I'll be covering the simulations. Now this is just a cursory simulation in SOLIDWORKS of what a 10 Newton force does with the stress distributions on isostress. And another important part, of course, remember, is the fatigue. Because this will be cyclic loading, there's a lot of frequencies and large amplitude displacement, because we will be using a large pitch spring, a very high pitch spring, in order to compensate for the lack of stiffness that nitinol exhibits. Next slide. Now, as far as the prototyping is concerned, we really don't have too much machine costs and such, because we are exploring using rapid prototyping techniques such as 3D printing in order to cut down on our costs, as we are making a scale model. We're not making a full scale model just yet due to cost constraints, because we are funding it by ourselves at this point. We are exploring those possibilities, but I'll cover that later. Nitinol will be molded and annealed at approximately 500 degrees Celsius in order to train it. We also are exploring about changing the transition temperature in order to compensate for environmental factors such as the latent heat and also the ambient air temperature that is experienced by vehicles and such. Simulations are going to be a little bit difficult because they are non-linear. Nitinol is a lot non-linear material, it's not linear, so we are going to explore ANSYS and try and incorporate that. We're having a little bit of difficulty getting that model, but we are exploring that. Also, the thermal delivery system, we are trying to engineer that as we speak. We haven't quite finished with that yet, but we will be exploring that soon. Next slide. This is our overall cost analysis, just a rough cursory one. Next. And our timeline. These are the possible outcomes. Our expected is that this is successful and we become millionaires. Unexpected is that failure to determine fatigue due to the property materials, and failure in the as far as the dynamic response that we're hoping for. Those are our unexpected. Next slide. Global considerations. The standard will be English and SI units, instruction manual, multiple languages. And we're hoping that this will be a low maintenance option for places that are not accessible. As far as material sourcing is concerned, we have local and overseas sourcing. Next. And you can see our advantages and disadvantages as far as shipping times and pricing. That's about it. Next. And any questions?
You're planning to make the nitinol components using 3D printing?
No, the housing. We plan on ordering stock wire and training and annealing it ourselves. We're going to be making a fixture out of brass to anneal the spring into shape. That's going to be our primarily our only machining cost, but based on the scale we're using at least.
Okay. Martin heard you say nitinol in the shape memory form, which is what I assume you use.
Yes.
Is impacted by a few things. The AF temperature is directly impacted by contamination. In other words, very, very small changes in carbon content will cause hundreds of degrees change in those temperature. So you have to be very, very, watch out, very, very careful to keep that material very pure. So that's it. Okay, the other thing is the transformation is also strain induced. So you're using it as an actuator. So you can actually cause the material to transform by the load applied. So you're going to have to be able to look at that too. So you've got the thermal effect and the stress effect going on with that material. I understand that?
Yes, that's why we chose the shape memories, because we were expecting that the latent heat generated, that the heat produced by the strain would be able to absorb some of the energy from the system, thereby reducing the vibrations that's in the system.
But yeah, that's all got to be played into this thing. And the last thing is, throw this out, Abacus has a nitinol modeler that you may be able to.
Actually, my partner can get a little bit on that, because he explored that.
Yeah, we've been playing with Abacus. We found that SolidWorks has a dedicated model for nitinol in the custom material section. This is for shape memory alloys. What we do is we measure the tensile stress. We find A star, A finish, which is Austin and Martin's side, all the curve, as you see in the poster. We find the points, and we insert that into the model. So it calibrates to that type of material that we are using. So
how do you find those points?
But when you go through the simulation, and after you've measured this whole thing with those points right, and you start going through your cycle, it's the simulation model has to change.
Right.
And SolidWorks doesn't do that.
Right, and that's why, so we're trying to explore that, because we know ANSYS and Abacus, but ANSYS is the one that I am learning currently, so I'm trying to rely on what I know right now. And that they do have some sort of subroutine that you can implement in order to anticipate the behavior of nitinol, because it is such a strange animal as far as materials are concerned.
Okay.
I'll just follow up on that really quick. Yeah, I mean, you should definitely investigate the explicit form of whatever you're using. If you guys are interested, we'll talk more about it. But it all has to be time dependent and strain dependent.
Right, and that's why in our unexpected outcomes, the dynamic response is key. It is one of the baselines for this tool. If it doesn't, then we're kind of dead in the water. But there's not a whole lot of literature out there that we can find on this.
Yeah, right. So you'll have to, you have some curves associated with the mechanical properties of your specific alloy. You'll need explicitly your alloy's curves, right? So somehow you're going to
That's correct, and that is the real issue with nitinol, is that it really is material dependent, but not the material, also the lot and when it was made and impurities, etc. So we're trying to take that into account, and that's why we don't have anything really specific to nail down right now, because we don't have material just yet.
Following the abacus comment there, once you do your analysis, your FA analysis, as you're testing your prototype, and you get a lot of data from the software, are you going to also back up those numbers? You know, are you just going to rely on the software, or are you going to actually do hand calculations to confirm the numbers that you're getting off of the software is correct?
Actually, we did provide some screenshots of an Excel document that we generated as far as calculations that were done by hand, such as this. These are all standard spring maker formulas and such, and to find the spring rate and spring diameter, and the standard empirical formulas that we have, we do have. So we're not relying strictly on analysis. We are trying to back that up with models, the analytical models that are generated.
Initially, what we're doing is we calculate the endpoints, the minimum and the maximum, because in between, we're trying to use the simulation to see in between. Since we assume that it's going to be 40 gigapascals and 70 at the end. So we also thinking to research how it behaves linearly or non-linear, so we can see the behavior in between those points.
What's the difference between your little K and your capital K?
There was a typing.
Is that a typo?
Yeah, typo. Yeah, it's a typo. It's the same K, but since K is
Good question. It is a typo.
Yeah, it's a typo.
What's the global aspects of this project?
The global aspect of this project is that it's anticipated to be low maintenance, because it's the standard shock absorber uses a fluid-based shock absorber that changes the velocity of the fluid in order to absorb the vibrations of the system, the energy in the system. And this basically is just another set of springs. So there is no fluid, there are no valves, there is very little relative frictional motion, and we're expecting that because you can change the K value, that is also more versatile than the standard shock absorber or standard damping system. That won't cost as much. That's the anticipation. But due to all the variables, we have to kind of explore as we go on.
Yeah, I have a couple of questions on this. First thing, why do you want to make a spring? Springs are readily available of this material.
Springs are readily available, but not in the scale. Generally, the springs are for small automotive purposes, the nitinol springs, such as for cylinder heads and such, and also for medical applications, and they're generally very, very small. We're talking on the orders of wire diameter of 4 millimeters, 5 millimeters in diameter, and that is not really, those are not currently manufactured. And the reason why we chose this specific material is because of its properties. Initially, we spoke with our advisor and explored ternary alloys in order to basically produce an alloy that has every single property that we desire and leaves less to the imagination as far as what the materials are going to be. However, based on the scope of our senior project, this is all we have time to do. And we believe that this will allow us to get a conclusive result within our time constraints.
You are going to propose this material as a shock absorber. And so you keep on saying the word damping. So what's the loss factor you have for this material, and how does it compare with the other candidate materials which are being used as shock absorbers for this application?
Well, as far as solid shock absorbers, we haven't really found any that are comparable. As I was saying, the standard shock absorber is a fluid-based, and we're trying to do something that's not fluid-based. So we don't really have anything to compare it to at this point in time. We have found some literature survey that there is, that nitinol does attenuate vibrations in certain medical applications such as implants in the mouth, teeth and such, but we don't really have too much by literature survey on that. I can just-
How much nitinol itself has a 10 delta, the loss factor?
Excuse me?
How much the 10 delta, when you talk of damping, you can tell that modulus is a loss modulus and a storage modulus. The ratio is 10 delta. How much is the 10 delta for nitinol?
I don't know.
Do you understand the question?
I understand what he's saying as far as the loss factor and storage factor, but I don't know. I don't know what the factors are.
We have a part on the testing, which is going to be, we're going to put an input on the system, and we're going to measure the output. We're going to measure the transmissibility, and we're going to find how effectively it can damp the vibrations, and then get the ratio from there. We haven't got to that point yet, but we're still trying to build this table so we can purchase the right geometry and then build a prototype